Okay, so we are back at it, and I think this will be the last video of our semester here. We're going to talk about hardware for liquid chromatography. In other words, we're going to detail all the individual parts of a liquid chromatograph, which is the instrument used for chromatography. So I'm going to start talking to you about the pumps for liquid chromatography. Pumps actually play a key role because we need to pump our mobile phase liquid through our column. If we don't achieve that at a consistent flow rate and very high pressure, the experiment's not going to work out. So what are some desirable characteristics of fluid pumps? Well, we want it to be chemically inert for a wide variety of solvents. Our pump cannot react, it can't rust, things like this, okay? We want our pump to achieve constant flow rates. This is important. Just like the oven in GC needed to keep a consistent temperature, our pump in LC has to maintain a very, very consistent metered flow rate, usually in the milliliter per minute range. We don't want our pump to pulse. Now, you probably don't know what that means, okay, right? But pulsing is actually like the sinusoidal behavior in terms of output flow over time. And we would rather it just be very, very stable over time, okay? And that's what we mean by pulsing. Our pump also needs to have high pressure capability. I mentioned several thousand PSI is required. And that's for standard liquid chromatography. If you go to this high pressure, what I mean by high pressure is stuff that's evolved over the last decade with tiny little particles, okay? If you go to those types of experiments, even smaller and smaller particles, you may need to go to tens of thousands of PSI, very high fluid pressures. We'd also like our pumps to have the ability to use gradients, to run gradient chromatography, because we learned all about the advantages of gradient chromatography there at the tail end of the last video, how you could change the composition of your mobile phase, and in doing so, during the experiment, you can get late eluting peaks to elute on. So what are some pumps that people use for liquid chromatography? Well, the two main types are a reciprocating piston pump and a syringe pump. In my experience, the reciprocating piston pump is by far the most common. The way this works is it's going to be a sort of electromechanical device in which there's a piston attached to a rotating cam. Now that piston and cam are right there, the brown and green respectively. And there's going to be a couple of these sapphire balls that basically are going to make one-way valves, okay? Now, let me blow up this picture, and I'm going to explain it to you as best I can here, okay? So first off, down here is where we're going to have our bottle of our mobile phase. And the flow, after passing through the inlet filter, is going to go from bottom to top here. We're going to pull it into this device. The pump actually sucks the fluid in. So how does that work? Well, as mentioned, this cam is attached to an electric motor, and it consistently rotates. And when that happens, this piston basically moves back and forth in a cyclical pattern over and over and over again. Now, in here is a chamber full of fluid. We're basically going to sequentially fill that up and dispense it over and over and over again as that cam and piston move back and forth, okay? Now, how can we make this work? Well, the key to doing this is these devices. This is called check valves. And there's two of them. You can also call these one-way fluid valves, okay? They only allow fluid to move in one direction, from bottom to top, onto the column. Now, how do they work? One of them is right here. What we see, if we look closely, is that little red piece, which is meant to represent a sapphire ball. They use sapphire because it's chemically inert. They engineer out a little divot or conical section there in that ring, and they call that the seat for the valve. And it's engineered to just the right size and dimension so that that sapphire ball can potentially sit in that little divot, okay? Now, if that sapphire ball sits in that little divot, it seals off that valve. But alternatively, if the sapphire ball is not seated in there, if it kind of comes out of the seat and floats around the solution, then that valve's open. And you can see it right there. There's a little retaining screen to keep that sapphire ball inside this apparatus, but allow the fluid to pass through the little holes in the screen, okay? We have a very similar, actually exactly the same device up top, except it's kind of installed backwards relative to the one at the bottom. We've got our sapphire ball, we've got that little conical divot. If the ball seals, that valve is sealed off. If the ball comes loose, open, okay? Now let's think about an entire pumping cycle, starting with the piston moving backwards. When that piston begins to move backwards, I'm increasing the volume of that chamber, the fluid-filled chamber in through here. And that basically reduces the fluid pressure in there. So what's going to happen is it's going to want to suck fluid in, right? Almost like creating like a fluid vacuum. And it's going to suck fluid in from the bottom through this tubing, so from the mobile phase bottle reservoir through this tubing. And now what's going to happen, since the low pressure exists in that fluid-filled chamber, this sapphire ball will unseat and fluid can move in freely to the chamber. And we can fill up the chamber. Okay. Now, before we go on, let's think about what will happen at this top valve during that reverse stroke. During the reverse stroke, the fluid pressure in here, we said, will drop. And if that happens, there might be an instantaneous influx of fluid back this way, but that sapphire ball sits in that seat then. It seals during the reverse stroke of the pump, doesn't it? It seals off. No more fluid flows. But fluid can flow from the bottom up, thereby filling up our chamber. That's how we get fluid from the mobile phase reservoir into that inner part of the pump. Now think about the opposite stroke. So the cam pulls the piston back, it reaches the maximum displacement, and now it's going to come back this other way. Okay, what's going to happen then? Well, all of a sudden, I'm going to start compressing my fluid in that chamber. The fluid that's in there is going to start experiencing a high pressure because I'm really forcing it out, right? So look, this top valve will then open and the fluid can flow around the sapphire and on out to the column, which is out here. Actually, the ejection valve and the column's out that way, okay? But down at the bottom valve, once the high pressure generates in here, that sapphire ball will sit right in its seat and be forced there, pushed against that seat. On the forward stroke, that valve is closed. So we have this sequential opening and closing of these one-way valves with every stroke of our piston. And what we're able to achieve is one-way flow from the mobile phase reservoir out of this pump onto the column, where we can do our separation. This device, called a reciprocating piston pump. And now you can understand why. It's a piston that reciprocates over and over and over again. Again, creative names for things, right? This is the most common fluid pump used for common high-performance liquid chromatography. It can achieve several thousand PSI at a reasonably consistent flow rate. Now, the only problem historically with these pumps, people still use them all the time, okay, is that these pumps by themselves will produce sinusoidal pulsing in the detector signal oftentimes because they are pulsy, and that originates from this piston basically moving back and forth, different cycles, right? It makes a lot of sense if you think about it. Of course, you're going to have this sinusoidal pulsing with this type of pump. What you can do is add a long piece of tubing called a flow dampener, or a pulse dampener, excuse me, between the pump and the column, and that helps deal with this a little bit. But nonetheless, these pumps can be pulsing. Now, the other type of pump is called a syringe pump. This is an example of a syringe pump, however, is not one that you would use for liquid chromatography. This is just for general purpose dispensing. If this was for liquid chromatography, the syringe, which is right here, would be a little bit larger, and it will probably be made out of stainless steel, not glass, okay? So it can withstand much higher pressures. But nonetheless, the idea is kind of the same, so the visual is useful. What happens is we take a syringe and we fill it up with solvent. This one's almost empty, okay, because the plunger's right here, but we would fill it up with solvent, a large volume of solvent, hopefully. And then a screw drive inside here basically pushes the plunger to dispense the fluid over time. Syringe pump, easy enough. They're commonly used around the lab to provide a relatively constant rate of flow. The cool thing about the syringe pump is it does indeed provide a more constant rate of flow. The bad side to it is that you have to refill these after emptying out the syringe, right? You dispense, then you have to take time to refill it. It takes a little bit of time. Whereas with that reciprocating piston pump, as long as there's fluid in the bottle, you are good to go, okay? But nonetheless, this is syringe pump. Now, the next thing I want to tell you about is how to get the sample into your chromatograph. This is done through what's called an injection valve. And again, this is one of the things I think is really cool. An injection valve looks like this, if you ever see one, okay? For liquid chromatography, this is a side-on view of one. And right here is a little piece of plastic. Now, it turns out what you do is you inject your sample using a syringe right in that center hole or center port, okay? That's where you're going to add your sample using a syringe. Usually you use a needle with a flat tip to do that, flat tip needle, and that's different than GC, which is a sharp pointy tip needle. But nonetheless, the volumes involved are different too. You might inject hundreds of microliters into this valve using one of these flat tip syringes. And it turns out it doesn't matter all that much what you inject for reasons that I'm going to describe to you here before too much longer, okay? So let's talk about this, all right? Let's talk about how this works. Okay. Well, if you're going to use one of these injection valves, you're going to take a syringe, and actually in this particular case, this is plumbed right here, okay? And dispense your fluid sample into the valve when the valve handle is in what's called the load position. When it's in the load position, the fluid from your injection syringe is routed through this chamber of the valve, out through this piece of tubing, back through here, and off to waste. Follows that red route, okay? Now this is when the valve is in the load position. Very important. There's two positions. One's called load, one's called inject. In the load position, that's the fluid path. Now you look at this, and you're probably confused. You're saying, okay, I'm injecting all this sample, but all I'm doing is routing it into the valve, out of the valve through this other piece of tubing, and then off to waste, right? Like, how do I get it in the chromatograph? This doesn't make any sense, but it will in a second, because what we just did in this step is we filled up part of the chromatograph called the sample loop. Sometimes this is referred to as the injection loop. Sample loop is also common. And all this is, it's not very exciting. It's just a piece of tubing, okay, like stainless steel tubing. In fact, in this diagram, you can see the sample loop right there. It's just a piece of tubing. And you say, well, let's fill up that piece of tubing. Like, what in the world are we doing here, right? Well, it turns out that that tubing is always the same volume from run 1 to run 3 to run 5, always the same piece of tubing, isn't it? So that sample loop has a fixed and specific volume. So wouldn't it be cool if we could use that sample loop as a way basically to measure a specific volume that we're going to inject onto our chromatograph? And it turns out that's what we're going to do. Because once we're ready to inject, we take the valve handle and we turn it, 1/8 of a turn or so, maybe a 1/4 turn, into the inject position. This is where we actually physically add our sample to the column. Now what happens? When we switch the valve manually, or sometimes it's electrical, the entire fluid connections within the valve change. Okay, let's look what occurs now. So after we go to inject, the syringe is routed directly to waste. It's out of the fluid flow completely. So it's completely insignificant at this point, okay? But the other parts, that's what's important, because now we want to add our sample to the chromatograph, right? So over here, I would have my pump. and I would plumb the tubing from my pump up to this inlet right there. Pump solution through there constantly. The solvent would go in through here. This is my mobile phase now. Enter my pump here through this port. This is called a 6-port valve, by the way, because it's got 6 ports, right? Fancy name. That fluid's going to go through my sample loop, back to the 6-port valve, through that spot, and then on to, lo and behold, my column. So look what I've done. I pumped fluid back through the sample loop and onto my column. So the point is, any material which I load onto that sample loop will now be injected onto my column. And in fact, the loop volume determines the sample which you inject, and only the loop volume. So it doesn't matter if you take your syringe and you inject 5 milliliters. In the first step, all that excess is just going to go to waste. And all you're going to be left with is what's contained within the loop. And that's a kind of a wonderful thing because it sets our injection volume each chromatographic run to be standard and similar each and every run, right? And we like that because that allows us to do quantitation. I mean, you can't be injecting different quantities of material each run and expect to measure anything. It has to be a very precise, reproducible injection volume, and our sample loop allows us to achieve that. It's quite creative, I think, okay? But a lot of injection in HPLC is done this way, using this type of injection valve. Now, let's assume that we can separate our molecules on our column. And again, I told you many of the different modes of chromatography. The column itself is just a small bore tube, usually made out of stainless steel. The column is probably 10 to 25 centimeters in length. Commonly, you can get longer ones, maybe up to half a meter. Obviously, the longer the column, probably it's going to take you longer to achieve the separation just to get the peaks to elute. You pack that column, is generally using pack columns with the types of materials we talked about last video, okay? But once the analytes get to the outlet of the column and they've been separated based on the mode of chromatography you're using, we still need to detect their presence. How do we do it? There are many different options. We can use a light absorption detector. We can use refractive index detector. We can even use fluorescence or amperometry if we want to. In ion chromatography, we tend to use conductivity detection almost exclusively. That measures the electrical conductance of the solution as it elutes from our tube. And that makes a lot of sense because ions can alter the electrical conductivity. So why not use conductivity? There's also a general purpose detector called the evaporative light scattering detector that's able to detect compounds which are less volatile than the solvent in the mobile phase. Okay, so there's lots of different options. I'm just going to tell you about some of the more common ones. Now, in my experience, the most common detector for LC is a UV absorbance detector. This measures light absorption. Remember we talked about Beer's law, A equals EBC? That's what we're talking about here. Absorption of light by compounds, usually organic molecules. UV absorption detectors will respond to any and all compound that will absorb down in the ultraviolet. Now, you can buy different models of these. Some of them are based on diode array technology that we also talked about. And there you can get complete spectrum, basically, every half second or even faster. That's very powerful because you can get the absorption spectrum of the analyte as it elutes from your column. But if you don't have that type of detector, you might have a single wavelength detector. What wavelengths will you use? Well, a lot of these analyses are conducted at 254 nanometers because that turns out to be a spectral line emitted by mercury in mercury lamps. So it's kind of a convenient wavelength there around 250. And it just so happens that many organic molecules will absorb that wavelength. So it becomes kind of a general purpose tool at 254, okay? Now, many times you can have a monochromator in your absorbance detector. You can actually adjust the exact wavelength. Commonly done, you can change it to match the absorption spectrum of your analyte. Again, very, very commonly done. But once you decide on what wavelength to use, you take your UV-Vis light source, perhaps pass it through a lens and a window, and then you pass it through a cell that looks something like this. Okay, this is kind of just meant to be instructive, I suppose. It doesn't have to look exactly like this, but it's just one example. And so what we see here is that there's a housing for the detector, and the light basically passes through two different channels. One is here, and one is over here. Now, why are they different channels, okay? Well, in the bottom, we've got a reference solution, which is essentially going to serve as our blank or 100% T. So that 100% T is going to contain our mobile phase, basically, at the time of the experiment. But this top channel is going to be our sample channel. And what we're going to do is we are going to pump our solution from our column in through the inlet. And this is the actual sample in the mobile phase. It's going to come around this way, back out to the outlet. This is a flow through optical cell, isn't it? That's all it is, a flow through optical cell. But when our molecules elute from our column, they're going to pass through that. And if they absorb ultraviolet radiation at the wavelength that we are using, that light absorption will be noted by ratioing our I to I0. That's our T, right? Transmittance, which is basically the signal on the sample channel reference to the signal, light signal intensity on the reference channel. Okay, so this device can be used to measure percent transmittance and therefore absorbance through mathematics, okay? Very simple device. These are very, very common. Oops, I don't have the other ones in this set of slide, do I? I guess not. Okay, I'll just have to kind of describe the others, I guess, verbally real fast. Thought I had all those. This is the most common detector. Okay, really quickly then, the other detectors, refractive index. This is a general purpose detector that can detect more or less all analytes. Because what we're sensing in the refractive index detector is an ever so slight change in the refractive index of our sample when analyte molecules pass through a detector. Now, the refractive index is basically a measure of how much particular material, we'll say, will bend a light ray or refract a light ray when it encounters a beam of light. And that's different for different materials. Different materials have different refractive indices. So we use this property to our advantage, and we actually build a detector that measures that. And the great thing about that is it is extremely general purpose. You can measure just about anything. Problem with it, not so sensitive, okay? It's kind of like the TCD of the LC detectors. Not super sensitive because this mechanism of detecting just doesn't lend itself to a huge instrumental change or signal per unit concentration. Not super sensitive, okay, but general purpose. Now, the next type of detector is fluorescence. Remember we talked about fluorescence. It was when molecules go from the ground state to the excited singlet state through absorption of a particular photon. And then after vibrational relaxation, the molecule emits light as fluorescence. We talked about that. There are these other vibrational levels here that we got after the absorption, we got the first vibrational relaxation, right? But then fluorescence resulted from a singlet state. Now that fluorescence can also be used as a detector for liquid chromatography if the molecules of interest are fluorescent or fluorescently tagged. So if our molecules are so-called natively fluorescent, which means that the molecules themselves, which are the analytes, they can fluoresce and undergo this process and glow, give off light. Well, why not just build a fluorescence detector to detect them directly? If we have a light source, maybe even a laser that emits at a very specific wavelength, which is absorbed by the analyte, we can focus down that laser beam to a very, very small spot on our chromatography, on the outlet of our chromatography column through an optical cell there. And at a 90-degree angle, we can measure the glow or the fluorescence. Easy enough. This is a fluorescence detector. These tend to be quite sensitive. Because again, fluorescence is a very, very sensitive method. Now, if your analyte's not fluorescent natively, you may need to tag it. Fluorescence tagging is a common approach that can be coupled with LC. And what that basically means is before you even do your chromatograph experiment, you take your analyte solution and you derivatize it with fluorescent tags. You make the molecules fluorescent with a reaction. And I remember telling you about that back when we were talking about fluorescence. Okay, so I won't expand on it more here. Amperometry. We've seen this before. This was one of our electrochemical methods. This is where you measure current due to a redox process at the outlet of your cell. You just sit there with the working electrode. That working electrode is biased at a particular potential with your 3-electrode potentiostat, and you measure the current due to oxidation or reduction of your analyte. Now, of course, your analyte needs to be so-called electroactive, just like our molecule needed to be fluorescent to employ fluorescence detection. Here, our molecule needs to be electroactive. And of course, what we mean by that is able to undergo a redox process, either oxidation or reduction, within the mobile phase solvent, without that mobile phase solvent interfering in any way, okay? Amperometry, also very, very, very sensitive. If you want a specific application of amperometry, look back to when we were talking about electrochemistry in one of those lectures on the website. I remember telling you about an amperometry-based detector for liquid chromatography. At that time, you can see figures. You can even probably find that in your book if you want to, okay? But that was an example. Now, conductivity, as I mentioned, we're usually going to use this for ion chromatography. Almost always for ion chromatography, it employs a conductivity detector, and that's because ions conduct electric current. And if you change the concentration of an ion, say as during an eluting peak from a chromatograph, an ion chromatograph, conductivity will change. So why not use that property? And lastly, the evaporative light scattering detector. And this one is also fairly general purpose. And basically what happens in this type of detector is at the outlet of the column, whatever flows out of the column, whatever elutes from the column, right? So we say it flowing out of the column, it elutes from the column. Whatever elutes from the column is basically, you create a fine spray out of it, and then you evaporate the droplets, hence evaporative, okay? You evaporate the droplets of whatever elutes from the column. Now, if you've just got a solvent, like maybe for our purposes, let's say it's a mixture of pure water, okay, with acetonitrile or methanol, something like that, okay? And you can even add some methanol into the mix if you want to, just for talking, right? This is your mobile phase. Now, these solvents are generally pretty pure when they're used. They're high-grade solvents. They're relatively pure. They don't have a lot of impurities. Now, if you take a mixture of all these liquids and you create like a spray and try to increase the temperature to evaporate everything, what are you going to be left with if it's just a pure mixture of these? The answer is nothing. They will all evaporate and turn into a gas. So all these, during the process of evaporation, are just essentially evaporated to a gas. Now, I say, well, how do you detect anything then if you just evaporate everything to gas? Well, you know what? I did not consider an eluting sample, did I? So now we're going to have another molecule that's going to be in our sample. Now, it's possible that that sample molecule also has a very high vapor pressure and it will evaporate. But it's also possible that that molecule has a lower volatility. In other words, it doesn't readily evaporate into the gas phase. So if you have a solvent with the sample molecule dissolved within it and you evaporate off the solvent, what are you left with? Well, probably just solid particles of this stuff, whatever it is, right? Sample molecule, I'm being general here. So if you evaporate off the solvent, the high volatility solvent, and your sample molecules are lower volatility, you might just like crystallize that stuff out and make tiny little solid particles. Well, if that's the case, you basically made this aerosol of tiny little solid particles. And all you need to do to build a detector, real simple, get yourself a low-cost laser beam, almost like a laser pointer, right? We'll call it a laser rather than a laser pointer, just to be scientific. But a low-cost laser, not too much different than a laser pointer. And you shine that laser at that series of particles which were produced after the evaporation. And of course, those particles will interact with the laser beam and scatter light, won't they? So all you need to do is at some angle, I'll suggest here for the purposes of our discussion, 90 degrees. Maybe you put yourself a PMT or a photodiode, some sort of light detector that we learned about this semester. And that will sit there and collect that scattered light. The intensity of the scattered light will be proportional to the aerosol concentration, which hopefully is proportional to the amount of sample molecules present in your sample. Thus, the light scattering signal can be linked back to the amount of analyte present in the original sample. Now, evaporative light scattering detector is pretty sensitive. It's also pretty general purpose because any molecule which has a sufficiently low vapor pressure, it's not volatile, that you can make these solid particles out of, any molecule that will do that when the solvent evaporates, you can detect via this method. So that's a very general purpose, okay? All right, so these detectors, I kind of given you an overview of all these. Maybe I'll try to find some videos online that explains each one a little bit more so you can kind of see it in action. But that's more or less all that I really want to talk to you about with regard to liquid chromatography. All right, so what I'd like to encourage you to do is make sure you read through the chapters in your book all about separation science and chromatography to maybe fill in some loose ends, things I didn't get to in lecture or just didn't talk about. I think that would be instructive to you to learn about this because like I said, chromatography is a very, very, very popular method for modern chemical analysis. And the more you can know about it, probably that you're better off, okay? So with that said, I'm done with lecture. Like I said, I might try to find a few more videos just to fill in some blanks here. Your final exam's coming up. That's the only thing that we have remaining. So make sure that you set your clocks, iPhone alarms, whatever kind of phone you use, to make sure that you remind yourself of that final exam time so you don't miss it. We have to take it at the official Texas Tech time for the class. There can be no exceptions to that. Texas Tech schedules out the final exams to make sure there are no conflicts. And that's why we do that. And we're going to hold to that. Okay. Should be no reason why we missed the final exam. I'm going to make the final exam over the material. I'll say from the whole class. Okay. But I'm going to try to put a focus on this last portion of the class because these are things you haven't been tested on. And, you know, they're really important for modern analytical chemistry. In terms of things you'll need for the exam, as usual, a calculator. I'm also going to let each of you use a note card, 4 by 6 inch. Whatever you want written on it, front and back. We'll need some scratch paper. There will be some calculations, most likely. You'll need something to write with. So I'll put writing device, pen or pencil, right? Whatever you prefer. You will need a photo ID. And you will need a computer that's able to use the Proctorio software, which means you need a webcam and microphone, okay? Make sure that Proctorio's set up well in advance. And with that, I think we're ready to take this exam. I've enjoyed having you all in the class. I hope you found something useful out of it. I hope you found the format also convenient for you as you continue your studies in chemistry here at Texas Tech. Thank you all, and we'll talk later.